So all of that was just introducing these two functions. And so the deal is that it's really easy to write straightforward code for these. So let's take a quick look. So here's high common bits. All we're going to do is walk through the bits in the input. And here I'm assuming a 64-bit input. We're going to walk through the input reversed, so from 63 to 0. And every time we see two bits being the same in A and B, we copy that bit to the output. As soon as we see two bits at the same position that are different in A and B, we set that bit position in the output and return it. And low common bits is just the same. The only thing that's different is we loop from 0 to 63 instead of 63 to 0. But we do exactly the same thing. We're copying bits in the output as long as they're common between A and B. And then as soon as we see a difference, setting the bit and returning. So what we have here is a really slow implementation. So even if we translate this implementation straightforwardly to C, it's still going to be really slow compared to optimized implementations. So optimized implementations of this are going to be potentially more complicated and potentially harder to get right, but they might execute in just a handful of clock cycles as opposed to maybe 100 clock cycles for the optimized C versions and probably thousands of clock cycles for the Python. So of course, performance isn't really going to be our concern here. We're just using this to illustrate an issue that comes up in extremely optimized try codes. So the fact that we're trying so hard to optimize these codes means that we're going to have some concerns about whether they're correct or not. So let's talk about how we're going to deal with that. So what we're probably going to do is write a random tester. And the reason we're going to write a random tester is with 64-bit inputs, the input domain for either of these functions is going to contain 2 to the 128 elements. So it's far too big to exhaustively test. We're going to be forced to do some sort of either systematic testing or random testing. There's no way out of partial testing of these functions. And so the most obvious kind of random tester to write would be make a random 64-bit integer, make another one, and now assert that our super optimized high common bits function called with A and B returns the same result as a reference implementation. And I showed you the Python version, this sort of simple, incredibly obvious code. And maybe a reference implementation is C. It doesn't really matter. We're just going to randomly test all sorts of configurations of this function. So the question we need to ask is this a good random tester? And what we might do is run the code coverage tool. So let's go ahead and do that.